Hi everyone. All right, today we have a couple of examples here on linear, and I'll deal with that one first with this first example, and angular speeds, which I'll deal with angular on the next example. And just by definition, a particle moving at a constant speed along a circular arc of radius r. Okay, it's just going around and around and around, a particle where s is the length of the arc traveled in time t, has a linear speed, we use v for that, of s over t. So there's the relationship. S is the arc length, t is the length of time that it travels that arc length. Okay, let's use the clock here. A second hand of a clock is 8 centimeters long. Find the linear speed of the tip of the second hand as it passes around the clock face. So if I go here and I just draw, if I start up here at 12 o'clock or at 12 and go all the way around, okay, it'll take 60 seconds to do that. So we kind of know the speed there. And so that's the time. That's the 60 seconds. So the linear speed in 60 seconds. Well, how far does that travel? This is an 8 centimeter second hand here. And it goes around once. So it goes around 2 times pi times 8 centimeters. 2 pi r is the entire circumference, and it does the circumference in 60 seconds. So when we give that answer, let's get the calculator out here. We're going to give the answer in centimeters per second, because that is the units we have here. How many centimeters does that second hand go in per second? Each second. So we'll take 2 times, I'm going to ask you guys to use the pi button. It's the second function of this. I don't know if you can see that. Second function of this one right here. Times 8 divided by 60. And I'm getting 0.838 centimeters. So a little less than a centimeter each second is how far this travels as it goes around the clock in 60 seconds. All right, that is linear speed. Okay, I am now going to deal with angular speed, and we might even do another part with linear speed as well. An angular speed, if theta is the angle corresponding to the arc length s, so in other words, let's have a circle here. If I have this arc length s, theta is the angle from the center, the central angle that intercepts that arc. If theta is the angle corresponding to the arc length s, that would be this kind of relationship, then the angular speed of the particle is, and this is a curvy w, that's a lowercase omega. It's the measure of that central angle, whatever theta is, over the time it takes for the particle to get from here to here. Theta in this setting is in radians. All right, so a circular blade on a saw has a radius of 4 inches, and it rotates 2,400 revolutions per minute, so it goes very fast. Find the angular speed in radians per minute. Okay. Well, it is going around 2,400 times each minute. Okay? Well, that in radians, one time around is 2 pi. It's going around 2,400 times. This is one time around. Multiply that by 2,400, and then your time is 1 minute. Okay, so this is in radians, which is 2 times 2,400 is 4,800 pi. And I'm going to leave it like this, radians per minute. Now, if you think about that, 4,800 times 3.14, that might be close to 15,000 radians per minute is what this is approximately. All right. Now, it's going that fast. Well, the angle is changing that fast. This angle up here, how fast is that, like a particle, like the edge of the blade, how fast is that changing? And I'm going to say it's really fast. So let's look for that linear speed. I need you to know that the arc length is r times theta, the radius times theta. The radius is 4, and theta is 4,800 pi. So V, as we saw earlier, V equals S over T, and S is R times theta, which is 4 times 4,800 pi over the time of 1 minute. This is revolutions per minute. So, and the 4 is inches. So this is inches per minute. All right, so let's take 4 times 4,800 times pi, and I get 60,318.579 inches per minute. Now, just for a little perspective, and this is fine, this is the answer, 60,318. If I take 60,318.579, and if I divide that by 12, we're talking 5,026 feet per minute. And if, let's say, there's 5,280 feet in a mile, if I divide that by 5,280, that's almost 1 mile per minute. So that's approximately, 1 mile per minute is approximately 60 miles per hour. That's how fast that one little particle on the edge of the blade would be traveling. All right. We'll leave it at that, though. I just wanted to get a little perspective there. Okay, guys, you take care, and I'll see you.